Good afternoon, ladies and gentlemen. Welcome to IVS 2022 warm-up, the online technical conference preparing to IVS 4th edition. First of all, let me thank you all for coming here today. Let me introduce myself. I'm Virginia, one of VALVEcampus organizers. The topic of today's presentation is the sealing solution for cryogenic valves. The last minute of presentation will be the question and answer part. Please write your question in the chat box. It's now my pleasure to present Christian Salvatori, Business Development Manager, Energy MIA at VICTREX. Thank you so much and have a good presentation. Christian, you can start.
Hi everyone and welcome to this online technical conference. I am Christian Salvatori, Business Development Manager at VICTREX for the energy market. So today we will go through a new family of products recently developed by VICTREX, and I'm really pleased to present you the technical benefits of such polymers in cryogenic environments. So the focus will be on having a reliable sealing material in cryogenic valves for the LNG. So just a few words on myself. I have a physics engineering background, and I'm working in the oil and gas since the beginning of my working career in 2008. I started at Schlumberger as a seismic acquisition engineer on board of vessels, rigs in Western Australia, dealing with the data acquisition and processing while scanning the seabed for the research of oil and gas. And then after that experience, I worked for Saint-Gobain Performance Plastics as a sales manager, building a certain knowledge of soft seals for the valve industry until 2016, when I joined VICTREX. And at VICTREX, I'm focused on various commercial tasks, if you want, and I'm responsible of following various customers, especially in the EMEA region. But what I'm really proud to do is having the possibility of contributing in the development of new materials, either for existing or new applications, working every day to do our best to bring innovation to this market. So here you can see the agenda. The points we are going to cover in the next about 30 minutes is a brief introduction on who is VICTREX in energy and what's our mission. Then outlining the challenge and defining the needs in order to have clear in mind which challenges we address. Then we will dive into mechanical and thermal properties of cryogenic PEEK, putting the CT polymers in comparison with the PCTFE. Selection criteria for the best material. So let's say at this stage, it should be clear enough which benefits you can get by using the CT polymers and what are the differences between them. Then the summary and conclusion, and at the end I will be more than happy to answer any questions you might have. So VICTREX in energy, we are recognized as the #1 PEEK expert, either because we invented PEEK already 40 years ago, but I think even more because PEEK is the only thing we do. So all the VICTREX activities, all the strategies, market analysis, investments, research and development, everything, every single action we make orbit around PEEK. And how do we act in the market? Well, we think that the best way to serve every market we work in is actually to cooperate with all the supply chain. So in energy, for example, from our direct customer who process the polymer into shapes and parts, to the valve manufacturer who buys these parts for their valves, to actually the end users and the EPCs who needs these valves for their plants. So let's say that staying in touch constantly with the whole supply chain helps us to have a clear understanding of the needs everybody has, and to understand the trends of the market and the new opportunities we have to serve the market in the best way, creating new innovative materials and establishing partnerships to develop disruptive technologies. So all of these, including the CT polymers I'm going to present you today, is done with the aim to improve the product performance, for sure. So we understand how challenging your applications are, and we know how important it is to improve and innovate to address these challenges. Then increase the reliability, for sure, providing long-lasting solutions, extending also the lifetime of these solutions, and reducing the maintenance cost as much as possible. This, of course, this brings to improve operational efficiency and reduce cost. So just a number, we have calculated that 75 million of PEEK seals are in use today. This is a huge number. It's just one number indicating how much VICTREX PEEK has been and is now considered a revolutionary material, capable of helping companies who are striving to increase the productivity and to reduce the overall cost. So let's outline the challenge. Let's see which are the issues with the current non-metallic material exposed to a cryogenic environment. So they have a typically high coefficient of thermal expansion. It means that they are significantly changing their dimension as a function of temperature while the temperature changes. So which is something you would ideally like to avoid or reduce as much as possible when you design a seal, for example. They become brittle at low temperature, risking to break or to get damaged, and this would result into a leakage, of course. So you also don't want this. And there are several ways to test cryogenic valves, and let's say every cryogenic valve is a standalone case. So it's sometimes very hard to achieve certain repeatability of the performances. So there will always be properties, a differentiation in properties. Just to simplify, whenever you have a piece of plastic in contact with a piece of metal, you will have different properties, of course. And having these properties matching as much as possible would be the wish of every valve engineer. So it's clear that a non-metallic seal will shrink at low temperature, becoming less ductile. And both these factors will surely negatively affect the sealing performances of your valve. So either the shrinkage and becoming less ductile, it's a real issue. So this is a challenge for the non-metallic material. So now, PEEK, as you know, is well established on the market and recognized as a material used for high temperature typically and chemical aggressive application. And we know that for cryogenic sealing applications, PCTFE is the only material in use today, also modified PTFE, but let's say definitely more for the static seals or typically for very low pressure. So PCTFE would be and is actually the benchmark. The problem is that today, PCTFE is not anymore capable of covering the increasing range of temperature for the cryogenic valves that the cryogenic valves are seeing. It's become quite common that the end user asks for cryogenic valves which work from -196 to even +200. And consider that 400 degrees is a huge, very wide range of temperature to be covered consistently. So PCTFE is surely a material that doesn't help reducing the torque. It's not cheap and it has certain limitations. We believe that the market would benefit actually of a material capable of doing this. So extending the range of temperature, offering a more reliable sealing, because sealing in cryogenic valves is very, very challenging, lowering the torque, and allowing cost saving. This is something we aimed for when we developed the CT polymers. So let's start with a deeper technical analysis. One important point I'd like to bring to your attention is that the most of the data you will see are at -196 degrees. Why? Because this is where we need to evaluate the performances of sealing materials. So in light blue, you can see the CT100, the first cryogenic PEEK VICTREX launched already 4 years ago. And in dark blue, you can see the CT200, the second polymer launched a couple of years ago. And PCTFE is in yellow. So the tensile behavior is what we are looking at because it's a sign somehow of the ductility of the material. So it indicates how suitable it's a material for sealing. While we can see there are no big differences on the moduli at -196, it's possible to actually appreciate a significant higher strength and elongation as well. Significant, especially for CT100. So remember that the more ductile material will result into a more reliable sealing as it penetrates better the metallic counter surface, reducing the gaps and reducing the possibility of creating a leakage path for the fluid you want to seal. So this is a first technical analysis on the tensile behavior to evaluate the ductility, which is actually also confirmed by the next slide, this slide, where again, we have just seen on the graph the values. I apologize because it's quite a tiny graph, so it's not easy to read the values, but it's the same values we have just seen above here. So for the tensile strength, it's around 220 megapascal, and the tensile elongation of CT100 is around 8%, while the tensile strength for PCTFE is around 130 with a 3% more or less of elongation. It's important to underline as well that the elongation of 8% is a lot, because we are talking about almost -200 degrees and everything becomes very, very stiff. So an elongation of 8%, it's really appreciable. So here we see that the way CT100 breaks is completely different than the way from PCTFE, when PCTFE breaks. PCTFE breaks suddenly and pretty fast. On the left-hand side is shown the ability of CT100 to undergo more deformation. Also by looking at the microscope images, you can notice a certain plasticity of CT100. Again, all to underline the ductility of the material, which is very important. It's crucial when it comes to sealing capabilities. Having a material ductile, and ductility is never a simple thing when it's when the temperatures are going so much below the zero. So as expected, of course, both the CT100 and CT200 offer a higher strength, being at the same time more ductile. So a combination of properties which become even more important when if you have a relatively high pressure, let's say. So also the impact strength, it's quite important, and you can see that VICTREX CT100 had a 4 times higher impact strength, while CT200 has a 2 times impact strength. So it's either robust, more robust sealing, but at the same time is more ductile. Both of the materials, of course, CT100 we are seeing it's even better than CT200. Now, if we take a look to the compressive moduli, instead, we will notice that the three materials are comparable. So we see how in certain cases we have values 2, 3, 4 times better than PCTFE. For other properties, and like in this case, there are not big differences actually. So, however, as said, sealing performances are a balance of a number of properties, like strength, tribology, and besides the mechanical, also the thermal properties, for example. So let's start looking at the thermal properties as well. In this slide, it's shown the second biggest advantage of using CT100 or CT200 instead of PCTFE. So both the materials have in fact a lower and almost constant coefficient of thermal expansion, not only at the very low temperature, but especially as the temperature goes up. So the difference becomes more and more evident when the temperature goes up. So the graph shows data only up to the 50 degrees. The gap with the higher temperature can just increase. So, and we can stop the comparison around the 100 degrees or maybe 120 degrees, where PCTFE is not even usable anymore. So while PEEK CT100 and CT200 will continue to work properly up to 150 degrees, 180 degrees, 200 degrees, it's of course something depending on pressure. With the same behavior you would expect from a common PEEK. So there is no changes on the expectations you might have when we are talking about high temperature. So the changes have been made especially for the performances to allow the performances at the low temperature. So we refer to this when we state that CT polymers extend the temperature range of your cryogenic valves and reduce as much as possible any shrinkage or dimensional change. Now, the next slide, we take a look to another crucial thermal property, the thermal conductivity. So the thermal conductivity for both CT100 and CT200 is higher. So as we will never get rid of any dimensional change, what do we want? We want to reduce this as much as possible. But at the same time, we want it to happen as fast as possible. So in fact, the reaction speed of a polymer of changing dimension due to a temperature change is driven by its thermal conductivity. And the higher it is, the faster it will react. So this simply results into sealing consistency, especially while the temperature is going up and down. Your seal will follow its metallic counterpart more rapidly than what PCTFE would do. And this helps to secure your sealing at all times. Again, while for the mechanical properties, we have seen CT100 seem to be better, more ductile and more robust than CT200, we can see that regarding the thermal properties, CT200 is actually the best. And so it's here where CT200 comes to play a very important role, lowering the coefficient of friction, which means lowering the actuation force needed to operate the valve, which in cryogenic valves, it's often a challenge. We listened to our valve customer who were testing CT100 when it was released at the beginning, and they valued so much the mechanical and thermal benefits that this didn't stop us from improving more, let's say. On the other hand, it encouraged us to do more. And so we created CT200 in order to lower the torque and give the possibility to use a smaller actuator. After we released CT200, it was time to collect also data on its performances on field, so on a real valve. So we have started cooperating again with our valve manufacturers and customers to make a comparison test on a real cryogenic valve, stressing the material as much as possible, as much as we could. What you see in this slide is a significant example of testing our material in one of the most challenging conditions. Using a 10 inches top entry ball valve, class 1500s, from minus 196 to plus 120. We couldn't go higher because there was a PCTFE insert inside, and PCTFE cannot withstand, as we said, to temperatures higher than 120 maximum. And we made the TAT test as per the Shell Mask 77300, which allows for very low leakage rates. And we have measured the leakage and the torque. So we have noticed during the test a lower leakage over the whole range of temperature at each pressure. So despite there was some leakage, it was acceptable from the minus 196 up to 120. The tests have also shown that the torque in average was lower. So either at 2 bars or 250 bars, so low pressure or high pressure, if we see the torque given by PCTFE is at 1, all the times, all along the range of temperature, we had lower values. So to summarize, CT100 has an outstanding ductility and sealing capabilities with a great strength. CT200 has a better thermal properties, and a lower coefficient of friction. So when to use CT100 and when to use CT200, it's actually up to your needs. For example, if you look for outstanding ductility and you want to minimize the leakage as much as possible, probably you should go for CT100. When you want to minimize the torque instead, because you know you can use a smaller actuator, you may choose CT200 in the case. So if you want to reduce the wear, for example, as much as possible, you might go for CT200. If you have already hardened your ball and you know wear won't be a big issue, you might go for CT100. So it's really, it depends. You have seen outstanding mechanical properties for CT100, and you have seen better, even better than CT100, thermal properties for CT200 and the low coefficient of friction. If you have any question, I will be more than happy to answer your questions.
Christian, here is your first question. You have mentioned the possibility for a cost saving. Can you better explain this point and quantify it?
Absolutely. There are a few factors actually that should be taken into account. The first one is pretty much straightforward, and it's about the cost per kilo of CT polymers, which is in the same range of PCTFE. But considering that CT polymers have about 40% lower density than PCTFE, you simply need less material to get the same number of parts. So, for example, if you have to buy 10 kilos for making a certain billet of PCTFE, you will buy 6 kilos to get the same billet and therefore to have the same number of parts. So this is a simple matter of fact. Another one is more indirect, but not less important, of course, and it comes from the better technological performances. So having a material which lower down the actuation force of your valve, then the torque is lowered down, of course. This might allow the valve manufacturer to use a smaller, so a cheaper actuator, so they can sell a cheaper system. Other things are still linked to the improved technical performances. Lower the torque and lower coefficient of friction are likely to result in less wear or in an extended lifetime, if you wish, which is reducing maintenance cost. So that's why there is the opportunity for a cost saving.
Your next question is, would this material be suitable also for spring-energized seals or other sealing components apart from seat inserts?
Yes, despite the target application is CT inserts, there's nothing against using CT polymers as a jacket material for spring-energized seals, for example, considering that PEEK jackets are used in the seals market since decades, especially where a relatively high pressure like class 1500 or above characterize the valve. So in these cases, you might combine the robustness of a PEEK-based material with its outstanding ductility and low friction, extending the operating temperature of your valve from -196 up to the 180, 200, etc. So absolutely, the answer is yes. We don't have so many data, but of course, again, because we have targeted the CT inserts as the application, every other component which requires the same needs can be addressed with CT polymers.
Are you targeting other applications than valves for LNG for these materials?
So, as mentioned in the introduction, it's well known that hydrogen and CO2 application are already in the radar of the whole energy industry. So today we are moving in the direction of collecting data also at temperature below the -196, like for example, -253 or even below. This in order to be ready to support our customer regardless if it's a CT insert or any other components in the hydrogen production supply chain. But for sure, we expect our valve customer to ask for support in this sense, and that soft materials able to cover even a larger range of temperature.
Christian, what is the composition of CT100 and CT200, and in which form are they available?
Unfortunately, I cannot disclose the composition of CT polymers, but I can say that both of them are a PEEK. So within the family of the polyaryletherketones, they are polyether ketones. CT100 is an unfilled PEEK. CT200 is a PEEK compound with additives which help to lower down the coefficient of friction. CT100 is a natural color, and CT200 is green colored, which makes it quite unique and distinguishable among the common materials. In which form? CT100 is in granular form, so the typical pellet size you are used to with the common PEEK materials, while the CT200 is coming in form of micropellet, which is something in between powder, let's say, and the pellets themselves.
Christian, is the chemical compatibility of CT polymers the same as other PEEK on the market?
Yes, absolutely. There are no differences. The chemical compatibility stays the same of the common PEEK you are used to work with. This has always been a must for us, offering the market the possibility of having an alternative material which provides technical benefit at a lower cost, keeping all its other characteristics the same, for example, without compromising on chemical compatibility. So you will get the same identical chemical compatibility you expect and you are used to have with the normal PEEK.
Christian, your final question is, have you performed other tests than the one shown in our presentation?
So we have gone through an intensive and long-lasting testing phase at our VICTREX laboratories at some university we work with, and thanks to specific partnership we made with existing customers, either processors or seal manufacturers or seat manufacturers or valve manufacturers, to have a certain repeatability of the results obtained. And the presentation I've shown is the result of this work done in the past year. After this, the material has been released on the market, and in the last years we have collected several positive feedback from our valve manufacturer who shared successful results with us, which are in line with our value proposition. So we have a list of customers who already tested and validated the material for each size of the valve, from 2 inches up to 24 inches. And also the range of pressure varies from class 600 up to class 1500, for example. So we have proven the quality of the material and how good is the material, and that the behavior of the material is in line with what we expected on paper.
Thank you, Christian, for your good presentation. The time is over.
Okay, so thank you, Virginia, and thanks to the organizers. Thanks to VALVEcampus. And should you have any further questions, please don't hesitate to contact me. You should see my contact details here on the last slide. I wish you a nice day and maybe see you soon at the IVS next year in the 2022. Thank you very much. Bye-bye.
I wish you all a very nice day. Bye-bye.